Okay, so now we're going to start a Q&A session, and afterwards, around 4 o'clock, we're going to exit through our refreshments. So there are also poster sessions for some of our PhD students, which showcase the research done here by STAG. So, who would like to start? Just wait for the microphone.
I'd like to see who it is. This light is a pain in the ass. Who's asking the question?
Yeah, it's up there. Yeah.
Lloyd.
Well, I can't hear you. Sorry.
Sorry. Do gravity waves have any effect on the wavelength of light?
I still don't understand. What is he asking? Sorry, it's my ears, not your.
Do the gravitational waves have any effect on the wavelengths of light?
Yeah, okay. I see. Thank you for that question. I'm sorry I didn't quite understand it. And yeah, the question he's asking is actually a question that caused this technique, to be never funded until too late. Okay? Let me tell you what the reason is. The question he's asking is a really profound question. And it has to do with the fact that the same kind of trouble that Einstein got into when he made endless mistakes of his own in trying to apply his own theory. I'm not blaming Albert for that, but I'm blaming all of us, because when you make a theory that is coordinate independent, which is what the general theory of relativity wants to be, you should be able to use any coordinate system to express your physics in it. You can't necessarily believe the result that you have. You have to find an invariant way, and I'll get to answering you in a second, but that's the problem. You have to find an invariant way, a way that ultimately everybody has to agree on, independent of the coordinate system, that the effect exists. And now what he's referring to is the following. I'll give you the conundrum that is associated with that question. The conundrum is, people said, well, you can't measure gravitational waves this way. Why? Because the wavelength of light will get stretched the same way space gets stretched. That's the question. Isn't that the same? Yeah. That was prevalent everywhere. Well, it turned out you get into trouble if you do that, because you are mixing up two coordinate systems when you get into that kind of statement. And it turns out they cancel each other. Yeah, but it gives you a nonsense way of doing it. Let me give you 3 ways you can look at gravitational waves, but do not use them in any independent way of it. They have to be dealt with independently of each other. The first one is, this is the one Weber used and Wheeler used, which I didn't like, was there are gravitational waves, and what they do is they make a tidal force that pushes things apart and pulls them together. There is no curvature in space. You don't even think about it that way. Think of it as another tidal force. And everything else is Euclidean. That's one way. You can certainly get an answer. You don't get black holes well. You can't get strong gravitational fields well. That's another. Okay. That's one way to think about it. Under those circumstances, you could lose light and it wouldn't matter. The next way is to say, okay, let's make it so that there is no gravitational force. It's a different metric. I mean, the metric's the same, but a different coordinate system. And you say, okay, the propagation speed, the coordinate speed of light changes because you have changes in the geometry along the path. And that then, but the masses don't move. The masses stay at the fixed coordinate. That gives you a consistent picture also. And then the third way, which I think is the most pretty way to do it, and those of you who like to play with mathematics, try it for yourself, is yes, there's a direct interaction of gravitational waves with electromagnetic waves, which actually puts sidebands on the light. In other words, you can propagate an electromagnetic wave at one frequency, pass it through a gravitational wave, and what the gravitational wave does, it adds you're an electrical guy, so you know. You put FM sidebands, or phase-modulated sidebands, on the light. What are those? Those are little tiny sidebands whose amplitude depends on what is the strain in the wave, and the frequency is different than the main carrier frequency by the gravitational wave, on plus and minus omega gravitational around the carrier. And that, to me, is the neatest way of doing it, because you don't ever invoke anything but things that you already know very well. So that's my best answer to you. And the people who do it wrong will do it wrong by mixing coordinates. I'm sorry. Yeah.
Okay, any other? Yes, one up there.
Because there are waves are they reflected by any other entity? And if so, what
Just
object?
like he was coughing, I can't hear you. Say again, please.
Because these are waves, are they reflected by any other object? And if so, what properties should the object have in order to be imaged with the gravity waves?
Okay, stay standing up because I want to make sure I understood you. You're asking what might scatter gravitational waves. Is that the question you're asking?
Yes, for imaging.
Right. And so let me say a little about that. That's, again, a very interesting problem you can do for yourself. You don't have to accept my explanation. And what you do is do it first in electricity and magnetism, okay? And calculate the scattering of matter, the scattering of electromagnetic wave by intervening matter. And how do you do that? You calculate the dipole you induce in the electric dipole that you induce in the molecules that are in the way, and then you look at what they re-radiate, okay? And there's a forward term that looks like an index of refraction, and if it's not organized right, the gas is all in different places, like in the blue sky, you get scattering all around. That same process works for gravity, of course. But the problems are the numbers. It's not that the idea doesn't work. The problem is now you take and let this gravitational wave propagate through matter, and that induces, let's use the tidal way of thinking about it. That induces motions in the matter, which are quadrupolar, pushes matter apart this way, pulls it together. You calculate the quadrupole moment of that, in other words, how big a source of gravitational waves it is. And you find out you're talking about a scattering of 10 to the minus 40. 10 to the minus 40 for typical kinds of things. Of course, it depends on the mass. But the cross sections are so small that you can take gravitational waves and send them through the whole universe, including the very beginning, and never see that scattering. So we look at the gravitational waves as though they are penetrating, beyond belief. It's also another way of saying why they are so hard to detect. They don't do anything. Yeah, sorry, that's the best answer I can give you.
Yeah, there was another one to the right.
In a similar vein, does that mean gravitational waves, do they not lose energy?
No, that's not true. The ways what he's asking is do gravitational waves lose energy as they propagate? Well, there are two ways of talking about that. If you integrate, like you do with light, and you have an intervening medium and it's not scattering, if you take light, you find out if you integrate the light over all the places it can go, and ask how much intensity is over every little piece of area all the way around, you don't lose energy either. And that's what you have to do. On the other hand, if you look at how much energy there is per centimeter squared of light, it's getting smaller and smaller as you get further away from the source. And that's certainly true in gravity also. In other words, the geometric spreading out of the beam certainly exists in gravity as it does in electricity and magnetism or acoustics. So it gets weaker, yes. But if you integrate over the whole sphere that the light is going into, you don't lose energy into something nebulous. It just gets diffused, that's all. Yeah.
Will what you've done give us more insight into dark matter?
That's a good question. He's asking whether doing this kind of astronomy with gravitational waves will tell us better what dark matter might be. I've looked at that somewhat. I can't be honest with you and say it will do something, but let me tell you what kind of things have to be so that you would get something out of that. It might be that Lisa, I don't think, and again, I'm guessing here. I don't know how to do better than guessing at this. I know it's terribly hard to already do measurements of the dark matter density amount. You see pretty much, I don't think it'll add much to what people are doing now, but I'll tell you the idea in a second. What's being done now is people are looking at clumpiness, the clumpiness of the dark matter in lensing experiments, and experiments where you are looking at a light from a star or a galaxy, and you'll notice that there's lensing done by the dark matter. And that gets you some feeling of the structure of the dark matter, not on what it is, but what the density and the size of the objects are, the size of the clouds of dark matter. And I think there may very well be, not for LIGO, because I don't think we have the chance, but for LISA, they might be able, and somebody working on this thing should correct me on this. I know you have people here thinking about this, is that there might be clumpiness in the dark matter when they start looking carefully at the propagation, and they will be able to do the propagation of some of these very, very distant sources, and see if they have a phase fluctuation due to the fact that they're passing through different parts of clouds of dark matter. I suspect something like that, but I don't expect that we will actually detect the dark matter radiation itself. You know, the fact that it's being accelerated. I don't think we'll see that. LISA might have a chance, but it's very unlikely. So I don't expect we're going to learn much unless we learn something about cosmology in its entirety, which I hope we will learn. For example, I'll give you a thing that might be important. That discrepancy that's now seen between the Hubble constant for supernova measurements and cosmic background measurements. It'd be kind of interesting to see how the gravitational measurement of that comes out, and see if it can be explained by a decay of dark matter, for example. I don't know. I think it's going to be some part of the cosmological puzzle you will be able to solve better, because you have things with a completely different systematic error source than the things you do optically. But that's the best I can answer. I can't pick the problem and say, where is it that we're going to get something from dark matter? I think we have more to say about dark energy. I think that, but I think that may very well happen before we get to the very big experiments we like to do in the future. I think people are going to learn about the acceleration of the universe at a z of 1, at a redshift of 1. They'll probably learn about that from all sorts of optical and radio measurements that are going on or going to be going on in the next 10 years. I think, and then we will add to that, because we will be measuring all these black holes all the way out to the beginning of a z of about 30, z of 40, even, way out there, when the first stars get made. If we build the detectors, and I'll talk about that more tomorrow for the physicists. But the thing is that the ability to use the black holes as an indicator of what the universe is up to at very high redshift, very high distances, will have impact. And it may have impact on the dark energy and the equation of state of dark energy. But I don't think we'll have much impact on the dark matter. Not directly. I'm sorry, I just don't know anybody.
There were a question back there. I was going to say, you talked about the space-based interferometers and larger detectors, because at the minute our capability is pretty limited with LISA. Can you foresee in the future any larger interferometers being built in space?
Well, maybe I'll quickly show you that slide. That's what you want to do. Here. I mean, this is now for specialists more than... I didn't want to do it for a general audience because it gets kind of complicated. But what's in this picture is... This is where LIGO is now. This is, by the way, this is H as a spectrum, H per square root hertz. This is frequency, there's 100 hertz again about. And so what this curve, forget about that one, that's Virgo, and they're now better also. But here's LIGO as it was during the last run. And we're about to improve things so that we're getting down to here. Sorry, not there. Yeah, right there. That. And so that is where we should be. That's the advanced LIGO design. And that's what we hope to get. Maybe not this go round, although we're making improvements in the apparatus. Let me be absolutely frank with you. We never have quite understood yet the reason why we have not made design sensitivity in advanced LIGO. We don't know it as well as we did in initial LIGO, which is the one you saw with all those curves I showed you. We really understood that instrument after a while. We still are not at the point where we really understand this instrument. And we made a lot of changes this year. We'll hope that we get down to the design, but it's not promised yet. And we hope ultimately to get to the design. Maybe we have to do that within the next year after this. Then there is A+, which is this thing which is here. That's another thing that's done in the 4 kilometers. And these are big factors for rates, but they're not big factors for sensitivity. They're talking about factors of 2 or so. Then the plans for the future are, and I want to really stress these 2 things here. Here is a curve for something that might be done in the Einstein telescope. And that's the European idea. I won't go into what it is. And here is an American plan that is a little different, slightly better sensitivity. Well, these are all ideas for the future. And I will tell you what's the trouble with both of them. They cost a fortune. Okay, there's not been a real costing of those things. There are very clever ideas involved in them. But my guess is we're talking about $1 billion at least for each one. And that's big money. And that's not something you can get without a lot of rigor. We already had enough trouble getting LIGO right. So I expect that if the field advances the way I hope it does, and there really is a battle cry to be able to look at, and what's the significant point, and it's not a childish point. The significant point is that those advances will allow this field to go and do cosmological things. That you can't do with the 4 kilometers. These are things which are bigger than 4 kilometers and they're expensive. So, I'll talk a little more about tomorrow what some of the science might be that you could do with Cosmic Explorer, for example. Let me blunt and tell you what that idea is to make something 40 kilometers, an L of 40 kilometers on the ground. The Einstein thing is a thing to make a 10-kilometer equilateral triangle buried somewhere in Europe. I mean, that is an idea that was thought about 10 years ago, and maybe no longer quite the relevant thing, but they're going to do something in Europe which is such that Europe is along with whatever the United States does. I'm sure of that. So, but also those things are things that bring the field, especially black holes and neutron star physics, and some things we don't know about yet, but certainly those two will go into those detectors and be able to get to high values of Z. So that's the future, but it's expensive.
You mentioned earlier in your talk about primordial gravitational waves and how they'd affect the cosmic microwave background. Would the sources of these gravitational waves, would they still be black hole mergers, or would there be more different processes?
Yeah, that's a nice question. Thank you for that question. All the questions are good, I'll tell you that one. So the question you ask is, where might this primordial background come from? Well, you're asked to talk to this gentleman. He has one idea. And there are others, but the thing is that most likely, let me be absolutely blunt with you. There is some speculation that there are primordial black hole pairs. I rather doubt it. And I'll tell you what makes me doubt it is something from one of my colleagues, Paul Schechter at MIT, who gave me a conundrum that you have to figure out. He said if, and I know the proposal has been made by people all over that maybe you can solve the dark matter problem by letting them be primordial black holes, because you don't need to have a star to make a black hole. That's important. They can be geometric entities that don't start as a black hole that collapses, as a star that collapses to being a black hole. That's not necessary, because in fact the black hole loses the identity of what it was. Pretty much completely, although I know people place bets on that, but that's another story. So what happens is, yes, it could be black holes, but I'd rather doubt it. And more likely, what is the explanation is that they're not black holes colliding, but rather that in the very earliest phases, what some people call inflation, this is before the Big Bang gets reformed and makes a hot blob that then goes into the universe, we know that there are several ideas, one of them represented here by holography, another represented by people like Alan Guth and Steinhardt, that you have started the universe with an expansion that is unbelievably fast and has a particle that is a particle like a particle you might find in an accelerator. And this particle is responsible for the very fast expansion and is all quantum theory at that time because it's so small. And so when you start looking at what the quantum theory has for an organized system, at that time in the history of the universe, you find out it has many, many states. And that's certainly true in the holography thing, but it's also true in the other model. And those states represent different accelerations of matter as they go from one state to another. So it turns out there are sources in that expansion, in that very, very fast expansion, driven by quantum pressure, if you want to call it that actually make gravitational waves. So they are before the universe gets hot. And so those are the equations, and there are calculations for how big those fields ought to be, based on, in part, what is the current measurement of the anisotropy itself. I mean, what the 2.1, what the distribution of matter is in the universe now. Looking at where the galaxies are, you can get an idea what those represent, those quantum fluctuations. Because the dark matter made them, those density fluctuations that you see. So that's already representative of what might have been the case during that very, very early phase of the inflation. And a lot of people, including here, are thinking about how to correlate those things. So, yes, there is a great expectation to hope to find gravitational waves from that epoch. Let me tell you about the experimental situation as a physical measurement where you measure it. The only thing we have right now is this business of looking at the effect that has on the cosmic background radiation, namely the polarization patterns of the cosmic background radiation. That's something which is within the next 10 years. On the other hand, you people have already thought of how you might make an actual measurement, a direct measurement of that gravitational radiation. It was not in that picture that I showed at the end. This picture here does not have that. Why? Because it's pretty damn speculative. But yes, and there are people who have thought about this, and if you're interested in finding out about this, go to the web and look up Big Bang Observer. That's the name of the project. Big Bang Observer. You will find out what you have to do to get into the regime of sensitivity to be able to measure the high-frequency tail of that initial quantum fluctuations. They should still be there, but they're remarkably small. And that is it's a project that's orders of magnitude more difficult than LISA. Has to be done in space. Effectively has to take LIGO and put LIGO into space with all the bells and whistles of all the high sensitivities and so forth. You would look it up and you'll see it's not something you tell NASA that you can do tomorrow.
Any other question? Yeah, there is one over there.
Where are you? So I know.
Right here. My question's linked to the slide of the animation of the two neutron stars orbiting each other and then combining to become a black hole.
The what?
So,
If you can refer to a slide, which one?
The animation of the two neutron stars.
Ah, okay. All right. Which version of it?
If you keep going, keep going, keep going.
No, that's not new.
The animation, you have the animation when it's going around. I think it's.
Oh, the neutron. The animation. That's not neutron stars. Those are black holes. This thing, yeah.
Yeah. So when they combine to become the black holes, they're having the holes sort of going down through the space-time plane, whatever that is. It shoots up, and I was just wondering what that is.
Oh, okay. Yeah, you see it again when we get near the end of this. Yeah, I mean, what is that? Those are the distortions in space, the curvature that's generated. You're talking about the fact that there looks like water waves in space. Is that what you're talking about?
Well, no, what I'm wondering is why they go from one direction to then shooting up. Like if we just play this out and watch what happens.
I know you're talking about the very end when they come together.
Yeah.
And something comes up, but there's also stuff going, those holes are deep as hell.
Right.
Okay, it goes in both directions. I mean, so right there, that thing that's coming up on the right and left there.
Why does that happen?
Why does that happen?
Yeah.
I can't tell you that. I mean, it's not going up and down. You have to remember, but these are measures of the curvature of space. So it's really, I think that's a little bit of the fate of me having told you about the jungle gym. See, the jungle gym, the curvature is represented by a dimension that shouldn't be there, the z dimension. It's the same problem here. What you do is you find out that the space is extremely curved. And how do you do that? I can tell you how you do that. And I learned it when I tried to teach general relativity to people. That's the only way I could understand the damn thing. What you do is if you want to know if you're living on a curved space, and that's what you would do. You still might be in a place where things are two-dimensional. That's not the problem. What you do is you take a vector and make it travel along what are called the geodesics of the space of the shortest distance in space and time along in the space. And on the Earth, for example, if you only look at the surface of the Earth and not the three dimensions, just look at the surface of the Earth. If you had airplanes fly along, they are great circles on the surface of the Earth. They're not straight lines, okay? Because you can't go through the Earth with an airplane, okay? So it turns out that we know then that we live on a curved space by doing the following kind of measurement. You start with a vector and make it tangent to one of the geodesics, like take a start at the North Pole and start at the North Pole, take the vector and follow it and keep the angle between the vector and the geodesic the same. So what you do is you crawl along the surface of the Earth from the North Pole to the equator. Then you go onto a great circle that goes around the equator, around like that. Now this vector is always pointing at 9 degrees. You come over here, let's say 10 degrees over from the way you came down, and you go back to North Pole, always being tangent to keeping that angle fixed. And you find out, my Lord, the two vectors, you've done nothing, but the two vectors are at an angle to each other. That tells you you live on a curved space. That's what that is the intent of. Those pictures tell you that if you had done that experiment locally, you would find that angle bigger and bigger. That's all, as that height, that angle relates to the height of those waves. And that's as far as I can tell you what it means. Okay, why that happens, I don't know. The curvature is getting very big. Gravity is getting stronger and stronger when those things come together. That's the best I can do for you, really. And it's not a good explanation, I realize.
Hello, Professor. My understanding of LIGO is initially began with that the probability of can create gravitational wave is very small, such as the supernova explosion and the emerge of black hole, something like this. Also, the amplitude of gravitational waves is remarkably small, as you mentioned before. So, how LIGO can amplify the gravitational wave?
How what?
How LIGO can amplify gravitational wave?
We don't know. How do you amplify it?
Yeah, apart from interference.
Okay. We don't amplify it. We can't do that. We can't amplify it. It's out of the question. You mean make the gravitational wave bigger? No, we can't do that. But we can do things to make it so that what we're fighting all the time isn't to try to make the gravitational wave bigger. What we're finding, or the big fight all the time, is to use the gravitational wave that comes in at a strain of 10 to the minus 21. You're not going to change that number, 10 to the minus 21. You can't change that. But the thing you can change is the noise in your instrument. Okay? And what we do is, and I can tell you reams about that, if you get bored silly of that, was that we do all these tricks to improve the phase noise, the noise that is the ability to make a measurement of the phase of the light. There's a lot of noise in that, and we try to reduce it. We're even now beginning to use quantum theory of light to do it. It's called squeezed light. Light that hasn't got a standard Heisenberg limit in phase and momentum at exactly the same frequency. Turns out we have ways of doing that. That's a trick. Another trick is, so we have tricks, we use more and more light. And the more light you use, the better you can read the fringe. But that isn't our biggest problem. Our biggest problem is that things are shaking all the time. And now we're at a limit, in fact, in the detector that we're about to, in fact, we're very close to the limit, where the Heisenberg microscope, and I'll explain that in a second, limits the measurement. Let me explain that to you. It's already quantum theory. In the end, I can tell you the two things that determine our sensitivity are the quantum mechanics and something called the Newtonian gradients. I'll get to both of those. So let me start with, sit down, because you're going to get tired. The Heisenberg uncertainty is real simple. You've been taught quantum theory somewhere, maybe you haven't. But there's this wonderful way of getting with the uncertainty relationship, which is that if you try to measure the position of an electron very carefully, you louse up the measurement of the momentum, okay? Or if you measure the momentum very carefully, you louse up the measurement of the position. That's on many textbooks, and it's a wonderful example of what the problems are when you have to deal with quantum theory. We have exactly the same problem with these 40-kilogram mirrors. These mirrors are 40 kilograms. And we try to increase the light. More light allows you better definition of where the mass is, because it makes you have more and more light to measure the position. So you can measure smaller and smaller phase shifts of the light. And that is wonderful, but it causes a problem. All that light that you're using pushes the mass around. It's the same problem. The mass then gets kicked around by the momentum noise in the light. So there you are. That's the Heisenberg microscope on a macroscopic scale. So that's one thing we have to fight. Now we've got some very elegant ideas how to get around. You can't get around that delta P, delta X is always of order h bar or larger. That you can't do. But you use tricks. And one of the tricks is that at one frequency, the ability to measure the phase of the light dominates the noise. That's at high frequencies. And at low frequencies, what screws you up is the fact that the mass is getting kicked around. And so what you can do is you can change the noise in the light. You can make it have less amplitude noise at low frequencies, which pushes the mass around. And lots of phase noise. Phase doesn't have to be so well defined. And then at high frequencies, you can get a lot of amplitude noise because you're insensitive to the amplitude and make the phase noise much smaller. And that's called tailoring the quantum state of the light that is in the system. So that's one trick. And that trick we have to exploit, and more light, all that. Now the other one is a stinker. This is the gravity gradient noise. And that will set the limit for how well you can do measurements of this on the ground. It ultimately says you're going to have to do really big advances in this field by going into space. And what that is simple. Although we can do everything in the world to get rid of the seismic motions, let me remind you what the seismic motion is. So seismic motions, you're shaking up and down here because the water waves are hitting the shore. That's one of the reasons you're noisy here. Well, you can sense that. You can measure the amount of ground motion by the fact that you can use all the stars in the universe and use them as fixed objects and measure your motion with respect to the fixed stars. That's in fact F equals ma, you know, the thing you learn in Newtonian physics. You can always tell if you're being accelerated with respect to the fixed stars. So we do that, and you can do that very, very well. And you can do that better and better the more technology you use. And that's all the different tricks. But then you're stuck in the end with one problem you haven't been able to deal with. And that is the same thing that makes the ground accelerate, that you can make your motion with respect to the fixed stars about, causes another problem. The other problem is that these waves in the ground cause density changes in the ground. They propagate. So here's this mirror right there. And this mirror is sitting in a wave that is compressing the ground here, expanding it, compressing it. That, because the higher density of the ground over pulls the mirror over, just by Newtonian gravity. That disturbs that mirror, and there's no way to stop that. You can't put a block in, okay? So you're stuck. And it turns out the atmosphere does the same thing. The noise of the density changes in the atmosphere is much larger, but the density is much smaller. So there are two sources of gradients of density in the ground and in the air, which actually have Newtonian forces that pull on the mirror. And those cause a real problem. And that's why people, for example, in Italy want to build their system in the ground, underground. They think they're going to get less gravity gradient noise there. They may. We think that may be true, but then in the end, you don't gain quickly. They will do it, we'll find out. The Americans, on the other hand, think that it's hopeless, and they're not going to try to bury this because it costs so much money. You see, so you can see the differences in approach. But so those are the two factors. The one that's really the most important one is the gravity is the quantum limit, and the other one is the gravity gradient limit. Now there may be ideas you can think of where you measure the pressure in the atmosphere everywhere, you measure the motion of the ground's density everywhere, and you can correct a little bit the motion that you might impart to that mirror. People are working on that, but I don't think it's very promising. Okay.
Any last question? Last question.
When you look at the principles behind the Michelson-Morley,
I could not understand it. Sorry.
So when you look at the principles behind the Michelson-Morley interferometers and the LIGO interferometers, it's sort of quite a similar idea. Was there like a link between developing LIGO and looking at the ideas of the Michelson-Morley interferometers?
I'm going to have to ask him what you said. Straight up. What did you say?
Yeah, so the question is about the Morley differometer, about the speed of light, and the differometer you're using here. What is the differences and what is similar?
Boy, I don't even understand it from you. So, let's start again.
The Michelson-Morley experiment with an interferometer has similarities.
Yes, I can talk to that. But I thought you were asking a different thing, and I will get to that in a second. I failed to mention something very important at the end of the black hole business. The neutron star business. When you looked at that 1.7 seconds, I thought this is what you were asking, and it's related to it. That 1.7 seconds difference between the gravitational wave hitting us and the gamma rays hitting us, and that thing being 40 million light years away, tells you that the velocity of light is the same for gravitational waves and the gamma rays to a part 10 to the 15. So, Michelson-Morley could never measure anything that, but that's the separate story. Now, you ask why about if there is an ether drift. And it doesn't matter. I'll tell you why. And there are people who are proposing using LIGO as a way of doing the Michelson-Morley experiment over again. And I'll tell you why that's become sort of sexy nowadays, is there are new theories for Lorentz covariant and Lorentz invariance. I won't even pretend to understand what the problem is. But I know there are people making that a big industry, and that if you could really see a difference for the velocity of light in different directions, that would have strong implications for something. God knows, maybe you can tell me. I don't know what it is. But, so they come to us and say, can we use LIGO as a way of doing that? And it turns out that you can do no better, I don't think. And the reason has to do with the way we operate the instrument. We deliberately have to hold the instrument against the ground noise. The ground noise is so large that we have to hold the instrument, for those of you who know interferometry, we have to hold the instrument to 10 to the minus 10 of a fringe. We have to hold it, otherwise we lose sensitivity. There's servo systems, there are control systems that hold all the mirrors so that they don't move by more than 10 to the minus 10 of a fringe. That means 10 to the minus 10 of a wavelength effect, 10 to the minus 15, 10 to the minus 16 meters. Not 10 to the minus 18, 10 to the minus 16. And that gives you a dynamic range of about 100 still, where you can run the instrument and look for signals. Now, we have to do that, otherwise the thing is all over the place. You never hold a fringe. You have no sensitivity. And so it turns out that this same system that does the control of the positions of the mirrors so that they're in the right place to make the interferometer sensitive screws up any long-term thing, like, for example, you rotating the apparatus over 12 hours or 6 hours to see if there's a difference in the length of the apparatus that you measure with the light. We don't have any sensitivity for that, because we actually kill that out by holding the interferometer at that very tight tolerance of the fringes. So we're not a good instrument to do the Michelson-Morley experiment over again. That's what I'm trying to do.
Okay, let's thank Roy again.
Stuck it out, which is sort of wonderful. I'm delighted.
So we'll follow with refreshments and the Boston session outside. So.
I'm going to just